Hello, and welcome to today's Advanced T-Splines Modeling webinar about the new pipe command in T-Splines 3 for Rhino. My name is Matt Cederberg. I'm the CEO and a co-founder of T-Splines Inc. And I'm pleased to be joined on today's webinar with Tom Finnegan, who is also a co-founder here at T-Splines, and he was the lead developer of T-Splines 3 for Rhino and also wrote the pipe command. During today's webinar, Tom will help you understand the underlying principles of the powerful pipe command so you can better predict its behavior and get better models more easily. Before I turn the time over to him, I'd like to introduce our company. Since this is an advanced webinar, most of you in attendance are probably familiar with us, but T-Splines Inc. makes products that simplify organic CAD modeling in Rhino and SolidWorks, making it easier, faster, and more fun. T-Splines helps designers and engineers spend less time surfacing, create smooth, high-quality CAD models, and achieve the right look and feel. The pipe feature that Tom will focus on today really helps in all of these areas. Also, I'd just like to share one news item with you. You may have seen this announced, but we are holding a design contest this summer that goes until August 9th. The theme of the contest is Make the World a Better Place, so your entry should reflect that in some way. We have over 100 prizes donated by 3D Connection, 3D Systems, Chaos Group, SolidWorks, EnvisionTech, Evolute, GemVision, Luxion, McNeil, and Z-Corp. And the prizes include CAD software, iPads, and 3D prints of your model. If you register for the contest, which you can do today at tsplines.com/contest, you will be able to use free trials of popular Rhino plugins for the duration of the contest, including V-Ray, T-Splines, Evolute Tools, and Orca 3D. There are 5 categories to the contest: architecture, transit, jewelry, consumer products, and a miscellaneous category. And the architecture category specifically comes with a special offer. Z-Corp will ship 3D prints of the top 10 models during the contest so you can see your design evolve in real life. The first deadline to get a print for that comes earlier. It's July 5th. So again, go to the tsplines.com/contest to learn more details and so you can get started on the architecture category. So with that, let me turn the time over to Tom for the webinar. To formally introduce him, Tom Finnegan has been the lead developer of T-Splines for Rhino ever since its first release. As part of this, he wrote the pipe command, which he'll be presenting about today. And as a reminder, on this webinar, all attendees are muted, so please type in questions in the GoToWebinar panel on your screen and we'll type back answers throughout the webinar. Tom will also audibly answer questions at the end of the webinar. And this webinar is being recorded and you will receive a link in a day or two. So with that, let me turn the time over to Tom.
Thanks, Matt. So the goal of this presentation is to be able to understand the underlying principles of pipe so that you can predict the behavior and get better models more easily out of it. As part of this, I'm going to run through some of the design goals that we had and how we think that will help you in your larger modeling workflow. So the first thing that I want to talk about is the pipe basics. And really the best place to get an overview of how pipe works and what its different options are is on the forum. On the link on your screen, there's a video that runs through just very quickly all of the different options. On this particular webinar, I'm not going to spend too much time on the mechanics of how to use it. I'm going to spend a little bit more time on how it works, why it works that way, and how you can use that to make models. Just as a very brief introduction for people who aren't familiar with pipe, one of the biggest problems that we have with people coming from a traditional NURBS modeling background to T-Splines is the concept of topology is a very new and kind of tricky concept. And so we were trying to think of ways that we could simplify that concept. We could let users, for certain types of models, not have to worry about topology at all. And so we figured that if we let users start from curves and just build a pipe around those curves, we could automatically give them a good T-Splines topology, which will behave well and continue to be editable. So what the pipe does in a nutshell is it takes in a set of curves and then builds a pipe around those curves. There are all kinds of different handles that you can use to set the radii and get different models that might be good as a finished model or might be good just as a starting point for other editing and exploration. The next thing I wanted to talk about is the difference between the Rhino pipe command and the T-Spline pipe command. Here I've got 2 copies of the same curve, and if I run the Rhino pipe command on one and the T-Spline pipe command on the other, we see that we get very different results. So the Rhino pipe is on the left, and the Rhino pipe is designed for engineering. It basically says if I take a circle and I sweep it along this curve, I want to get that swept surface accurate to within a given document tolerance. And so what that means is that when you've got really long straight sections over here, it'll have very few control points. If you've got high curvature sections, it'll add more control points as necessary. With a T-Splines pipe command, one of our major goals was to make it user editable at the end. And we figure if you want something that's very precise that you're not going to touch again, then the Rhino pipe already exists and does a great job at what it does. So we decided we wouldn't try and reinvent the wheel here. This pipe, the T-Spline pipe, the cross-section isn't always circular, even to within tolerance. You can see here as it goes around the high curvature region that it's deviating from this center line, and it's also not the same radius. So we've got some behaviors that, if you're looking for an engineering style pipe, are probably not ideal. It also goes past the end of the curve, and I'll explain why that behavior is the way it is in just a second. One of the big advantages that the T-Spline pipe does have over the Rhino pipe is when you've got multiple curves coming together. So here I've got a Y joint with these 3 curves. If I do a Rhino pipe, I'll have to pipe each individual curve separately, and then now I've got these 3 solids that I have to try and figure out how to Boolean and fill it if I want that to be a smooth joint. With the TS pipe command, it's smooth by default. That's something that T-Splines does very well. And so you can just say, I want these 3 to go together. It'll figure out a topology for you that'll give you a nice smooth surface. So if we look at the zebra lines here, we can see, it gives us a very nice piped surface. So that's one of the big advantages of T-Splines and tsPipe is built to take advantage, to sort of do the things that T-Splines does well and highlight those. So the next thing that I wanted to do is sort of explain the basic steps behind how pipe works. And I figured the easiest way to do that is to do a 2D example. And most of the things that you see in this 2D example extend very naturally to 3D. There's a little bit of complication, but the principles are the same. So our steps are we split the curves, combine them into joints, select the prototypes, deform the joints, create the pipe meshes, and then create the final mesh. We'll go through each step here. So if my input is these 2 curves, the black curve and the green curve, the first thing that I'll notice is that this green curve is intersecting this black curve, or at least it's very close. So the first step, splitting curves, is it just goes through, find where the curves that you gave it are close to intersecting, and splits them up. The next step is it combines the ends of the curves into joints. And it does this by looking at each end to see if it's close to any other ends. So we'll see in this model, these 2 ends are close together, these 3 ends are close together, and this one end is not close to anything else. So in this model, we're going to have 3 joints. And the next step is probably the most complex step of the algorithm. But basically what we do is we say the user doesn't want to think about topology. What they want to do is just have a couple of different topological options. So we call these joint prototypes. And if we look at these joint prototypes off to the right here, we see that this first joint is going to have a single curve coming off of it. This second row of joints, each of them has 2 curves coming off, and they, this one is a corner, this one runs straight through, and so forth. So let's consider this joint here. We've got one curve coming off. There's only one option for a prototype that has one curve coming off. So we just move that into place and say that's the joint that we're going to use for that end of that curve. The next question that we have is, here we have a joint that has two curves coming off. And we have two options here to use a prototype. We automatically try and choose the best option. And the way that we do that is we look at what's the angle of these two curves versus what's the angle of the two prototypes, or between the curves and the prototypes. So this angle here is 90, this angle is 180. And we say that this angle is probably closer to 180 than it is to 90 degrees. So we choose that second prototype, we stick it in place, and then we rotate it so that it's as close as possible to the alignment of the curves. And then the last example here, on the curves we have roughly a 90, a 90, and a 180, and that matches this prototype best. So we do an instantiation of that prototype and stick it in place. The next thing that we do is we deform the joints. And there's a bunch of different reasons why you might deform the joints. It might be due to the angle of the curves coming in. It might be due to the user setting radius or twist or various other things. But specifically in this case, we see that the angle that this prototype is expecting the curves to come in is different than what's actually happening. So we deform the joint such that it's coming in normal to those connecting faces there. And then we need to sample these curves to create the mesh that runs in between the joints. So for example, if I've got this purple curve here, a part of the curve is taken up just by the joint, and then the rest of the curve is where I'm going to fill in with a pipe mesh. What I do is I take these curve positions and then take the curve in between them, and I try and figure out, based on the size of these joints, how many segments I should use in order to get as square as possible along the pipe meshes. That works the same way if I've got a longer curve. I just say, I want this this result to be as square as possible, and then build a mesh for each pipe. So I've got a mesh for each joint, which is built off the prototype, and then a mesh for each pipe. And the thing that's important to notice about this is that after I deform these joints, depending on the angles that these come in, and you can set different sizes and so forth, these pipe meshes are not going to exactly touch the faces of your joint meshes. So the last step is we just move the pipe mesh so that it touches the joint exactly, and we say that's our final mesh. I omitted the pipe mesh on the green, but you can imagine how that would work out. So that's about it. That is the basics of the algorithm and how it works. And so the next thing that I wanted to do is a demo of some of the advanced features and potential problems that you might run into as you're working with the tsPipe command. So let's open up Rhino here. And I'm just going to open up a very simple set of curves. So here we've got 1, 2, 3, 4, 5, 6. 6 very simple curves. And if we start the pipe command, we see that there's a couple of different preview options here. The boxed preview, in the box preview we can see very clearly, this is a joint mesh and this is a pipe mesh. If we change the preview to the box shaded, that's after the pipe meshes have been joined together. We can also get a smooth shaded preview, which can be useful if you're trying to set the different radii of this guy. So I'm going to give him a head here. Oh, that's a little bit big. To just sort of make a a cartoony shape fairly quickly. If I want to set multiple handles, I can say I'd like to set the radius for multiple of these guys, and make them both the same. The other thing that I can do is, these green handles that I have to change are ones that have been set. The blue ones are the ones that are automatically determined. So if I'd like to, I can also clear some handles. So, if I want these feet to go back to their original radius, then I just select them and then they'll pop back. And so I'm going to have my output type here as smooth. And there is my smooth T-spline model. Now, the nice thing about this is that it's a very light topology. So if I want to, I can go in and grab these control points and continue to edit. And it's fairly lightweight here. The other thing that we wanted to talk about is, is that this command can be hooked up with Rhino history. So there's a couple of different ways to go in and say I've set the pipe the way that I want it, and now I would like to change it. So if I select the output object and hit the pipe command, then it'll open it back up with all of my handles back in their original places. Here we go. The other thing that's kind of interesting is that we're hooked up to Rhino history, and every time we re-enter the command, it will exit the command with the history intact or not. So sorry about that. Right now this model is not hooked up to history, so if I grab the curve point inside this object and move it, the T-spline does not update. However, one of the things that's handy about being able to select the object and re-enter the command is if I hit the record history command and start tsPipe and just hit enter, say these are all the options that I want, because record history was enabled when I entered that command. Now if I turn on the control points here and modify them, it will recompute the pipe. So for this example, that's a very easy way to pose a figure really quickly. One potential gotcha with this history recording is if I save this and open the file, sometimes it will come in and it will convert this back into a polysurf. And if we look in the history, it'll tell us why that happened. It's basically a incompatibility issue that we're trying to work through with Rhino history. There's two ways that you can get this object back. The first is it says you can run ts-attach data, and that will in fact turn this back into a T-spline. The other thing that you can do is you can grab the any of these curves or any of the inputs to the history basically and modify them, and then that'll recompute the output and turn it back into a T-spline. Okay. The other thing that is good to be aware of with this modeling is often if these curves are offset just slightly from each other, so that if we look at them and they don't actually intersect, if I select them all and run tsPipe, we'll see that the result that it gives me is not what you might hope for right here. And the reason why is just because when it goes through and it's trying to say these curve ends are close to each other or these curves split each other, they're not close enough. So that's fairly easy to fix. We can go into the curve splitting, and I'll probably have to do a pretty large tolerance. It'll preview how many curves it thinks are coming in at each joint. So there we go. That gives us these 4 curve ends that are close to each other, and then that gives us the topology and surface that we're looking for. Okay. The next feature that I wanted to talk about is related to the prototypes. And the prototypes that we have that ship with it go from one curve coming into the joint up to 6 curves coming into the joint. However, let's say I have these curves that form a sphere. If I would like to pipe these, and before I show you my next trick, I'm going to go in and change this so that it's the fastest mode, because it can take a little while to compute these kinds of dense meshes. If I've got this curve here at the very top, I've got 8 curves coming in at one point, which is something that we don't have a prototype for. So I'll show you what the pipe command does in this case. Basically, what it does is it says if I've got 8 curves coming in, I'm just going to make a regular 8-sided polygon, so an octagon, and then thicken it and use that as my joint prototype. So it can place that fairly efficiently, and we can see the results here. This will work for any valence of, or any number of curves going in. It'll just create a regular polygon and then connect it. I see the question about does this command check for self-intersection of the curves? Oh, that's why it took so long, is because it was doing a smooth preview inside of the mesh. So you can see that it gives a very nice looking result here at the top. Let me switch this preview to box shaded, and there is our 8-sided polygon. Yeah, I'm not sure. It's been a while, honestly, since I've reviewed that code for the curve-curve intersection. We could do a quick test. So this curve does intersect itself. We run the tsPipe command, and it looks like it does not check for curve self-intersection. So you need to split that into 2 different curves for it to be able to automatically detect that. Yeah, so if you wanted to split that into 2 different curves, I would probably just use the split command. Select him and select a cutting object as a point here. I'm going to turn on my intersection snap and just say cut it right there. So there is 1 intersection, 2 intersections. It looks like I'll need to split that one more time. And let me see. Yeah, I'm not sure if tsSplit will do this either. tsSplit curves. And we'll see. Yeah, I don't think that's working either. So I'd probably just use the built-in Rhino commands for splitting this curve here. And for some reason this guy has not become unselectable. So that's always the excitement of live demos. Let's see. Yeah, but you can go in and use the Rhino split command. That should work fine. Let's see. Joint sense is the next thing we wanted to talk about. So here is a here we go. This is a fairly simple set of curves. We've got a rectangle with a single curve sticking out of it. And what we can do with the pipe command is if we get the default output, I'm going to switch this preview back to smooth shaded so we can see what the result is going to be. Actually, maybe box shaded might do this better. So we can see, the built-in or the default joint set will give me something reasonable. However, I can go over here to the current joint set, and I've got a couple of built-in different types of joints. So spikes, for example, will give me a spiked end. The more interesting joint set is the bendy joints, which will, if you give it straight segments, it will come up with a smooth curve in between those straight segments. And there's a couple of different options here for the joints that have 3 curves coming in, and I can try those different things out. The one thing that I wanted to show with this is that you can actually change the current joint set as you're setting different joints. So let's say, for example, I wanted this top to be a spike, I wanted this one to be a nice smooth joint, and then I wanted the other ones to be the L joints. What happens is, as I select the joint to change which prototype it's using, it remembers that prototype even when I change the current joint set. So if I switch this to spikes and click on the top, there's only one spike option, and then change it to square, which is the default. There you can see I've got my output object. Let me flip that guy. I got my output object, and it's got spikes on the end, and then it has the L joints and the bendy joint all together in the same model. Okay, and then the last thing that I wanted to talk about very briefly is the you can actually export from Rhino or from the tsPipe command the different prototypes that it's currently using. And I should give some caveats about this functionality. To be honest, it's not very well fleshed out, and the UI is somewhat lacking. So this is something that you can be aware that it's there. However, also be aware that it'll probably be changing in the future to make it more user-friendly. But this is very similar to the 2D joints that we saw. On the 2D joints, and let me switch back over to that really quick. On the 2D joints prototype, each one of them has, which edges have curves coming off of them, and then where the center point is. And that center point goes to the end of the curve, and then it aligns the edge with the curve as closely as possible. So that's the same thing here. Here we have a joint which is a single curve coming off of it. So we stick a point in the middle of the face to denote that that's a face which is going to be hooked into a pipe mesh. And then this point in the center is where it'll rotate around to try and find the best configuration. And so this is the built-in square one, and you can continue to make other joints if you'd like to, although the user interface is not ideal. And then let's see, the last thing that I wanted to say about this is that if you do, there are a couple of restrictions. One is that these meshes aren't general T-Splines at the moment, although that will probably change. They're just subdivision surface meshes. So any Rhino mesh will do. It won't pick up on T-junctions, and it won't handle the knots if you have them on your T-mesh. The other thing is that when they connect with a pipe, all of our pipe meshes right now have, the cross-sections have 4 faces. So if you want to make more joints, be sure that when you're sticking these marking points on the faces, that the face has to have 4 edges. And I think that's about it. So let's see, Matt, are there any questions?
Yeah, there. Well, first of all, Tom, thanks a lot for doing this webinar. I think we covered a lot of ground, and there are some questions. And if you'd like to see any other examples or review, please ask us. That was a lot of ground that we covered. Just before we get to the rest of the questions, just one note about the pipe command in tsPlines 3. If you're a tsPlines 2 user and you haven't upgraded to tsPlines version 3 yet, the upgrade price will go up at the start of July. So it's currently $200, and you want to go ahead and take care of that this month before that price goes up. And then also, if if you don't own T-Splines yet as well, then that price goes up as well at the 1st of July. So we'll be sending out an email just as a reminder to catch that before the prices go up. So some of the questions that we have here, let's just go back. So can you make a joint out of an arbitrary polyhedron, Tom?
Yes, as long as the face that connects onto the pipe mesh is four-sided. But other than that, it can be any arbitrary polyhedron.
Okay, great. Here's a question from Gwendolyn. Going back to your example where you had the auto joint on the top of that sphere, she says it only does the end-gone if the auto joints are turned on, right? Normally when I have more than 6 curves at an intersection, I get a wonky mess.
Yeah, so let me show that really quickly here. I'll just create. So here's a joint that's got 5 different curves coming in. If I run the tsPipe command on him, we'll see that the default here works well if the curves are arranged as faces going into a box, right? So in that case, you get something that looks pretty nice. However, if your curves are lying in a plane, so if I make another curve here and stick it off to the side and run the pipe command, by default, this is, I think, the wonky mess that you were talking about. It's taking that same topology and just sort of smashing it flat, which doesn't give you the type of surface that you're looking for. So if you did want to use the auto joint in this case, you can go into the joints option here, and there's one, always include the auto joint. And that also looks like it's not giving you, well, I guess it's not bad, huh? For the inputs, it's deforming this guy so that it'll try and fit them. And I think if they were radially connected, then it would look a little bit more like you'd expect. But if we look at the smooth toggle of this guy, it's actually a fairly decent looking topology. I see that Need says that he can't see the speed option toolbar icon in Rhino v5. If we open up this guy, the T-Splines UI, that's just the speed options button. You can click it on and it'll show up. The other 2 options that I had is I turned off the auto show and auto hide, so that way it doesn't appear and disappear. There's a question about the Cushball joints that we've been working on. The auto joints are great if all of your curves lie flat in a plane. However, if they're going out in all directions, sort of like a Cushball, right? The auto joints will try and flatten everything down. We haven't done too much work on the Cushball joints. It looks like those would only work on the higher valences. And we do have a method for producing those, but it's not implemented yet.
So here's just a couple of questions that were asked earlier. When the meshes around curves are also going to have a four-sided profile, is that right?
Yeah, that's correct. The joints assume that your pipe meshes are going to be four-sided.
Let's see, here's another question back to whether the command checks for self-intersection. I guess the question that Dave actually had is if you make like a radius too large that's too close to a joint, will it check to see if there's self-intersection with the surface?
Oh, right, if the surfaces are self-intersecting rather than the joints. I think it's actually fairly naive there. So if I run tsPipe on this guy again and change my built-in radius to something really big like 20, I think it'll just let you make what you ask it to make. So it's, if you set the options too large, you might have to manually check for self-intersection.
But the nice thing there, though, Tom, is that if you just make the radius a little bit bigger, it will adjust the joint, won't it?
Yeah, that's correct. It tries to make these parts of the pipe mesh as square as possible. And so if the joint is getting bigger by setting the radius, then it's going to have fewer segments. So it'll try and do the best job that it can as long as it can. Yeah, so here on this guy, we can see even though we've increased the radius quite a bit, it still gives a mostly non-intersecting. It looks like there's a little bit there, but for a dramatic increase like that, in general, it's pretty good.
Okay, so some more questions. The Kushbal problem describes exactly the problem we are dealing with, says Josh. How soon will you have a solution for this?
That's a good question. It's mostly in how long it would take to implement. I'm not sure if I have a good answer for that one right now.
So here's a question from Federico. Can you talk about T-Splines and Grasshopper?
So we did an initial T-Splines or tsPipe integration into Grasshopper. However, at that point, we didn't let you set things like the radius or the the curve position where things start. I've actually got an example of something that I think would probably be really cool to do in Grasshopper. This is a 3D Voronoi that I extracted the edges from. And if I modify this guy, I can, you can do a couple of things just with the Rhino interface in terms of, I'd like to set all of these radii to 4 and all of these to 0.2 or something like that, and get some really cool looking shapes. But it would be really nice to be able to hook into Grasshopper and say, I want to set these things as functions of, the distance or whatever. It looks like I might have gone a little bit crazy with that guy. Let me try that again. Yeah, it looks like that guy's not working as well as I had hoped. So I'm just going to clear all these. But yeah, that's the kind of thing that mesh is not manifold. Sorry for the distraction here. I think it's probably the auto joint is causing some problems, and it might be shrinking some joints down to nothing. So let's look at whether that fixes it. Okay. Yeah, so that was it. But sorry for the tangent. I think getting this all into Grasshopper would open up some really interesting possibilities, especially in terms of architectural sculpture and so forth.
And I'll just make one other comment about Grasshopper. This we talk about that fairly often here, and it just kind of keeps on getting crammed down further down the priority list. But if there is anyone on this webinar that is interested in using T-Splines and Grasshopper, we're just kind of looking to hear a little bit more clamor before we stuff more of this inside Grasshopper. So so if that's something that's interesting to you, please let us know, and we'll definitely push ahead on that.
Okay, I see a question here. Is there a way to set the radius of the joint independently from the radius of the pipe as a workaround to the Kushbal problem? That's a good question. I think there's a couple of different options here, and maybe what would work for to fix your specific example is you can set if we switch this to like the bendy joints here and set the radius, it sort of dies out over time, right? And so I think you can actually, all of the examples that we have in the that come with the T-Splines, the size of the pipes are the same throughout. However, there's no rule that your prototypes need to be uniformly spaced. You could deform the prototypes, and then when it, or have prototypes where it changes the behavior near the joint, and then when it deforms those, it'll honor those relative sizes. So that might be an interesting thing to look at. I'll see if I can work up an example and send one over.
Okay, so here's a question from Gwendolyn about set location on curve. Is it right that you can't set it right at 0.5?
Yeah, I think right at 0.5, the location along the curve here, if we do set multiple and curve position, this curve position is basically how far along the curve it is. So 0 is here and 1 is here, and this guy, he's maybe about a quarter of the way along, so he'd be 0.25. If you set them both to 5, then the pipe is exactly 0 width, and I think when we do some of the math, things get degenerate. We can't take cross products properly. So for that guy, you should be able to say like select these two and say 0.4999 will work. Just exactly 5 is too close, and if you set it over 5, then it's flipping inside out, which may not give you the result that you're looking for either. However, after the pipe is done, you can go in and manually move those control points if that's something that you'd like to do. Here it looks like they're almost stacked, but you could go in and actually snap them to each other or invert them if that would give you the surface that you're looking for.
So here's a question. Can we control edge smoothness with one click without adding extra lines? Do you interpret what that is asking, Tom?
I think that might be asking about things like creasing. And there's a couple of different ways to do creasing in T-Splines. There's the perfectly sharp creases, and you can set weighted control points. I think he's looking for something more similar to like an edge weighting thing that you would find in sub-D modeler. That's something that we're working on, but is not currently available. Probably the easiest way to do it right now is to just do the ts insert edge command, and it'll ask for an edge loop and insert geometry on both of those guys. That'll help sharpen up that edge. But that's not something that's built into the pipe command. However, that will give you a nicer looking model in some cases. If you want that more defined edge.
So here's a question. Can you control the distance between the faces of the pipe with size or scale?
Yeah, let me go ahead and make another version of this that doesn't have so many edits. I'll switch this back to the square option. And basically, between where this joint where this joint turns into the pipe mesh and where it turns into the pipe mesh, it's just trying to make this as even as possible. However, if you'd like to, you can set the segments. We select this curve center point, and we can say, I would like to have 3 segments, and that'll produce, what you ask for. So that'll give you a different, feel of the geometry.
Here's just a request to show how to insert an edge that doesn't go the full length of the model, just to do like a local insertion.
Sure. So let me grab, I'm just going to do one edge. And simple will make it change the shape, and that will sort of pinch it up locally, and then smooth it out over a couple of faces. Yeah, that is one nice thing about the T-spline or the T-points here is I can just have a local detail to give me some more definition where I need it, and then it smoothly fades off. The other command that you can do for the same sort of behavior is tsCrease lets you select an edge, and that will give you a perfectly sharp crease that then fades out over two faces. All of our commands here are working with Rhino 4, although they should also work with Rhino 5. There have been some bugs reported with piping in Rhino 5, which happens sometimes when they change. For example, I'm using the Rhino curve intersection routines, and sometimes the routines change between versions. So that's something that is on my list of things to do before the next release.
Okay, I think that we've responded to all the questions. If you asked a question a while back that they got buried. Oh, looks like here's one more. How does moving the handles up and down the curve affect the joint algorithm?
So let's see, if we do tsPipe again, it's these ones, right? So the joints know where they need to connect, and they'll try and deform themselves so that they can connect to those 2 points with the radius that you specify. In some cases, it's not possible. For example, in this case, if it were possible, then these 2 circles would be touching each other. However, here it basically does the best that it can, and then it snaps the other points together to give you a closed mesh. That's probably the easiest way to get a softer, more spread out joint. And that was one thing I was trying to show with the Voronoi example here. If we do the tsPipe command on these curves and set all of the curve positions to 0.3, then when we look at the output, it's going to be a very different feel, a much more organic and sinuous model. There's a question about, can you make the corner more round and radiused and less square? There are a couple of things that you can do by setting points. We also have some, Juan has worked up for us a different set of joint prototypes that tend to have better behavior as you're going in and out of the joints. So that's something that we're also looking at adding in a future version once we can get those working properly.
So here's a question: will we see a 2 star point mitered joint option anytime soon?
To be honest, I think if you have an example of that, that'd be very helpful in terms of figuring out what you're looking to see as an output.